So the idea here is that we want to find an inverse function for something like sine. So the issue is, if I have something like sine, this is not a one-to-one function, right? This fails a horizontal line test, so we know it's not one-to-one. So if I tried to find the inverse for this, it's going to look like this. Is that a function? No. So those of you that had my Algebra 3-4 class last year, we dealt with this situation. If we have a function that we're trying to find the inverse for that is not one-to-one, what did we do to the function in order for the inverse to be a function? What did we have to do there? We restricted the domain. So originally we started off with our function sine of x, whose domain is all real numbers, and whose range is -1 to +1. What we're going to do is we're just going to consider this part of our function. So the domain is now going to be from -π/2 to +π/2. The range, though, has not changed. In doing that, what we're going to get is basically this much of our inverse. So our inverse will now be a function. So we started off oops. Oh yeah, that's right. And when we make the inverse, does the domain change? Oh, I'm sorry. That's not right. The range here was all real numbers. It's down here that the range changes after we've done the restriction. Now, is there anything magic about the way we've made this restriction? Could we have done a different set of points to make our restricted domain? Yeah. We've really only chosen this part of the sine function to restrict our domain to by convention. So this is the same restriction that your calculator has programmed into it. So this is the idea. So the reason we need to do this domain restriction is so when we have this inverse function, it's actually a function. Okay? And that's what has to be programmed into your calculator. We can't program something into your calculator that's not a function because it has a really, at least the kind of operating system that like a TI-84 calculator has, is not capable of giving you infinitely many outputs for a given input. Right? It doesn't deal well with that kind of situation. Yeah. If you had like one of these fancier calculators as a computer algebra system, like if you had a TI-89 or something, it can handle doing that sort of thing. The unfortunate part is you can't use those on any kind of standardized test. So they're all on the banned list for like the ACT or AP test or whatever. So, okay. Does everybody feel okay with this restricted domain idea? Okay. So, similar things happen with cosine and with tangent. The thing that we really care about here are these ranges for the inverses. So just to kind of summarize, for sine inverse, the range is this. For cosine inverse, the range is this, and for tan inverse, our range is, I think this. I have to double check in my notes here, though. Almost positive. Yeah, okay. So that's the big takeaway. So any answer our calculator is going to give us is going to fall inside this range of values. And just keep in mind, like in calculator land, you know, pi over 2 is like 3.14 divided by 2. Right? So it's like 1.517 or something. 07? 07 maybe. I don't know, whatever. You guys get the idea. Because your calculator's not going to give you an answer in terms of pi, right? It's going to give you a wacky decimal. But that's the wacky decimal you're getting. Everybody's okay with that idea? All right, so if we actually want to start computing some of these inverses, and we want to do it without using our calculator, let's say we want to find the sine inverse of negative a half. Well, there's kind of two approaches I can take to this. You're going to need to be able to do either approach, because again, they may be, problems could be much, much easier using one approach than the other, so we really need to be capable of dealing with both kind of approaches. If I want to be able to do this without my calculator, one way of doing that is simply using the unit circle. So if I want to find sine of negative, or sine inverse of negative 1/2, I'm going to go and find places where the sine is negative 1/2. So which coordinate is sine on my unit circle? Y coordinate. So I see sine is negative a half here and also over here. Everybody agree with that? So my two answers would be 11 pi over 6 and 7 pi over 6 using the unit circle. Everybody okay with that? What's the problem here? Neither of these are actually inside of our range. Right? They're both bigger than half a pi. You guys agree with that? Okay. So, one way I could deal with this is I could just find an angle coterminal to it that does lie inside of that range. How do I find a coterminal angle? Add or subtract 2 pi. In this case, these angles, are they too big or too small? They're too big. So should I be adding or subtracting? Subtracting. So if I subtract 2 pi from each of these, from this one I get negative pi over 6, and this one I get negative 5 pi over 6. And that one does fall in our range. The other one is too small. So the answer that our calculator would give us is this one. Now, technically speaking, are all of these answers correct? Yes. They are all of these. If I take the sine of any of these angles, I get negative 1/2. The answer the calculator would give you is this negative pi over 6. Which, whatever that is, like around a half, I think. Okay. Method 2 I'm going to start by just noting what my range for sine inverse is between negative pi over 2 and positive pi over 2. That's these two quadrants here, right? Where negative pi over 2 is down here, and positive pi over 2 is there. And if we're increasing, we're going like and covering those angles. Everybody's okay with that idea? Okay. Now I'm going to go and think about all silly turtles crawl. In which of those two quadrants would sine be negative, because we have sine inverse of negative 1/2? In the second quadrant, down here somewhere, right? Now, I remember that sine is opposite over hypotenuse, right? And if I use the Pythagorean theorem, I can figure out this third side as the square root of 3. But remember that that sine of negative 1/2 isn't exactly opposite over hypotenuse. It's actually the x and y coordinates for this point on the terminal side of our angle. So here, the x coordinate is corresponding to the square root of 3. Well, that should be positive because I've gone to the right. And the y coordinate is corresponding to the negative 1. That should be negative because we've gone down 1 unit to kind of get there. Is everybody okay with that? Now, if I look at these side lengths, these look familiar. Those are the side lengths for a 30, 60, 90 triangle. Remember I recommended that we memorize those special right triangles way back in like the first unit. They're coming back. This is why it's useful to have. So this angle here is 30 degrees. When I convert that into radians, that's pi over 6. And to get to that terminal side, I need to go clockwise, which means it's really a negative pi over 6. Now, both of these methods are going to be important. We're going to need to be able to use both of them, and depending on the context, because you can take a problem and make it a lot harder or a lot easier depending on the situation. Notice that the first method relies on us actually having a value that's on the unit circle. If I had, say, sine inverse of 0.75, you're out of luck on method 1, right? Couldn't even try to use it because you don't have a unit circle value. We have to be using some kind of version of method 2. Does that feel all right here? We can make this a little bit sneakier by asking you guys to, or adding in a step and do something like this. Cosine inverse of tangent of 45. So when I'm given like a multiple, where I have like one thing embedded inside of another thing, where should I start? Should I start from the outside in or inside out? Inside out. Inside out. So tan of 45, I can compute that with the unit circle. 45 is here. Tangent is sine over cosine. That's just 1. Now, to figure out cosine inverse of 1, let's just go back to the unit circle. Cosine is which coordinate, x or y? X. So I'm going to look for the place where cosine is 1. Well, it happens in exactly one place here, right? When theta is equal to 0. And then the last thing I need to do is just to make sure that this is in the range of cosine inverse. And it is. So my answer is just 0. Everybody okay with that? So that wasn't so bad. So what do we mean by arctan? It's the same thing as tan inverse, just a different notation. There's a notation that was much more common like 30, 40 years ago, but still used here. Primarily when I'm speaking, I would say tan inverse, but you'll see in the problems here and there, arctan or arccos or arcsine. It just means the same thing as an inverse. Okay? So how many of you hope that it just, oops, that didn't make much sense. How many of us hope that just arctan cancels out tangent, we get this? That would be nice, right? What's the problem with this? It's not in the range of tan inverse. Well, we saw this before. Maybe I'll just subtract 2 pi, find something that's coterminal. Because it was clearly too big, right? 2/3 is bigger than 1/2. What happened here, though? Still not in the range. Ugh. Well, special, only for tangent. What's the fundamental period for tangent? Pi, right? Not 2 pi? So, what if we only subtract pi? And that is inside of where we're looking for. That was kind of cheaty, because that only works for tangents. If the same thing had happened with sine or cosine, you definitely can't just subtract pi and have things work out. What we can do instead, though, let's look at what the other option would be. The other option would be working from the inside out. So 2 pi over 3 is a unit circle value. If I find 2 pi over 3, that's here. Tangent is sine over cosine. So that's going to just be negative square root 3. And now I'm going to go back to my unit circle and locate the places where tangent is equal to the negative square root 3. So it's here at 2 pi over 3, and it's down here at 5 pi over 3. Because this divided by this is negative root 3. Everybody's okay with that? So I have 2 pi over 3 and 5 pi over 3. If I try to subtract 2 pi from this one, we know what happens. But if I subtract 2 pi from this one, we get what we're looking for, something inside of our range. Is this feeling a little bit clearer what's going on? I know that reading the book is sometimes hard, right? Hopefully seeing things happening live helps a little bit. Maybe? What if we wanted to do something like find cosecant of 2.5, or sorry, cosecant inverse of 2.5 using our calculator. Again, we'll talk about two methods here. So the first method, I'm going to use graphing to deal with this. So I'm going to graph cosecant of x, not cosecant inverse, just regular old cosecant. How do I type in cosecant into my calculator? Cosecant is related to which other trig function? Sine. What is cosecant? 1 over sine. It's the reciprocal. And then I'm going to type in 2.5. I'm going to make sure my calculator's in radian mode. I know mine already is because I just did this a couple hours ago. And then I'm going to do zoom trig. So here's the graph of cosecant coming in here. Notice the asymptotes all over the place. Here is 2.5. Everybody okay with that? So how many intersections do you guys see? 1, 2, 3, 4 of them. You guys agree with that? Okay. Which one of the 4 do I want as my answer? I need one that lies inside this range. This is the range for sine inverse. It's going to be the same range for cosine or cosecant inverse, Ben. So that's going to end up being the closest one to the y-axis here. So if we looked at our window, the x scale is 1.57. That's pi divided by 2. So this is like negative pi over 2. This is positive pi over 2. The only solution in there is this one. So how do we find that intersection? Second, trace. And which command am I going to use? Intersect. So to use intersect, we need to indicate the two curves that we're using. So first curve, where's my cursor at? There it is. That's good. Second curve, okay, that looks good. Guess. Here you're going to have to be careful. You're actually going to have to make sure your guess is really close to the intersection you want, because there's 4 of them, and unless you're careful, the calculator's probably not going to find the one you want it to find. So make sure you've moved your little cursor very close to the actual intersection for your guess. And when I do that, I get 4.12-ish. Or 412. Which is definitely inside of that range. Is everybody okay with that idea? So our second method, again, we're still going to need to use our calculator, but I'm not going to use the graphing function to do this. What is cosecant inverse? And what would it be related to sine inverse? Can I just do this? If cosecant is 1 over sine, can I just write that? Let's try it. Oops. Sine inverse. Uh-oh. What's the... Okay, so the error says domain. What's wrong with that? What's the domain for sine inverse? We just wrote it down earlier. -1 to +1. Why are we getting an error? Because we took sine inverse of 2.5. So can we do it this way, or did we just make a mistake? We just made a mistake. So cosecant inverse of theta is not 1 over sine inverse of theta. Cosecant inverse of theta is sine inverse of, I should probably say x's here, not thetas, because these aren't angles that we're taking, is going to be sine inverse of 1 over x. If I do that now, I get what I wanted, or what I was expecting. Should we unpack why I took the reciprocal of the inside part rather than of the inverse? So if I have y equals sine x, that would tell me that if I take the reciprocal of both sides, I would get 1 over y equals cosecant x, right? So if I do cosecant inverse of both sides, I get that, which would be the same thing as taking sine inverse of y. That's why we're taking have to reciprocal the inside part as opposed to the outside. If that makes any sense. That's sneaky. That would not be obvious without somebody showing it to you. I looked at that the first time I saw it and really had to think about that. Why you're taking the reciprocal of the inside rather than the reciprocal of the function. So if that's not super clear right away, let that sit for a bit. Come back and think about it some more. It'll start to make sense, but it's like you look at that at first and it's like, don't understand why that's true. Like it's easy, like I can remember to do it, but understanding why that's true takes a minute. And that little exercise I did there, I think, is one of the best ways I can do that, or explain to you why we need to do that. So the next example, we're going to find the algebraic expression for the sine of arc cos of 2x. Where should I start on something like this? The inside or the outside? Inside first. So I'm going to begin by thinking about 2x as a ratio. So arc cosine of 2x should give me an angle whose adjacent side is 2x and whose hypotenuse is 1. Everybody okay with that idea? So the answer to arc cosine of 2x is going to be this angle theta from this specific right triangle. Now I can find the third side of this right triangle using the Pythagorean theorem. So 1 squared is equal to whatever squared plus 2x squared. When I solve for that whatever, I'd get the square root of 1 minus 4x squared. Just using the Pythagorean theorem there. So what I can say then is that this is just sine of theta. Which theta? This specific theta from this specific triangle. How do I calculate sine? Opposite over hypotenuse. So that's going to be square root 1 minus 4x squared divided by 1, or just square root 1 minus 4x squared. So the idea there is we use the inside to build a right triangle, and then we use that right triangle to calculate the outside. So the single biggest takeaway here, the thing that I really want you guys to remember, that when we take the sine of an angle, we get a ratio of side lengths. When we take sine inverse of a ratio, it gives us back an angle. The tricky part about this inverse is that there's infinitely many angles that are really appropriate here. What's going to become maybe the trickiest part of this section is making sure that we're finding the angle in particular that we're interested in, of those infinitely many. Is that okay with you guys? Does that help clarify a little bit of what you might have read in the notes? Do you guys want to talk about the homeworks at all? Hopefully you guys had a chance to do, I think it was 1 through 18, is that right? I think that's what I posted for you guys. Valerie? 16. Yeah, can you read it to me? I like a moron, I didn't print off the questions. Okay. That's okay. Let's see, do I have it open? I do. Cosine or cosecant inverse of negative 1.5. So we did one very similar to this just a moment ago. Which method do you want to do? Do you want to do this by graphing, or do you just want to use the calculator to find the inverse? By graphing, okay? So I'll fire up my calculator. So I have 1 over cosecant already in there. And then here I'm going to type in negative 1.5. And I've already have the window to the normal trig window. But I think there's a little bit more to this problem I want to look at real quick. Ah, yes. So we want our answer on the interval from pi over 2 to 3 pi over 2. So if I go and I look at my window, I see that my tick marks are going up by pi over 2's. Right? 1.57 is like 3.14 divided by 2. So here's pi over 2. There's pi, and there's 3 pi over 2. So this is the part of the graph that I'm interested in, is this little section here. How many intersections do you see in there? Just this one, right? So it's between these 3 tick marks. There's only one intersection in there. You agree with that, Val? So that's the one we're going to go find now. So second, trace, intersect command. I can press enter twice here for the first curve and second curve, but for the guess I have to be very careful and move my cursor very close to that intersection because there's a bunch of them. If it's not close to that intersection that I'm actually looking for, it probably won't find the one that I want it to. So my answer there would be 3.87. Valerie, is that okay? Okay. Of course. Sydney, do you have a question on this one before we move forward to something else? Sure. So we're told in the problem that we want to be between pi over 2 and 3 pi over 2. When I look at my window, the way my calculator is set is the x scale is 1.57. That is pi over 2. That's 3.14 divided by 2. So this is pi over 2. That's the start of where I'd want to be looking for. That's 2 pi over 2, or just pi. And that's 3 pi over 2. So I'm looking for an intersection that happens in between these, or in between these two values. The only one that happens there is this one. You're welcome. Okay. Valerie, you also wanted to see number 6, you said? Okay. Let's look at what 6 is. Cosine inverse of -1. Would it be easier to do this? Would you, actually, I shouldn't say easier. Would you prefer we do this with the unit circle or by drawing reference triangles? I like that method better. Okay. So if I go pull up my unit circle, I'm looking for places where cosine is equal to -1. Which coordinate is cosine? X. So I look for a place where x is -1, right here, which occurs at pi. Okay. The last thing I need to do is check to see if this is in the range for cosine inverse. The range for cosine inverse is 0 to pi. So we're all set. We don't have to do anything to this one. Ah, yes, the range. Unfortunately, the ranges for sine, cosine, and tangent are all different. So you do have to be a little bit careful there with that. You feel good, though? Yeah. Good. So you got pi, you just weren't sure what to do with it afterwards. Yeah. Good. Who else wants to talk about any of these? Megs? 12? So sine of tangent inverse of 1. Okay. So we're going to work from the inside out. The first thing I want to do is find where tangent inverse is equal to 1. So I'm going to do that using my unit circle. So tangent is positive in the first quadrant and in the third quadrant, right? And tangent is sine over cosine. So pi over 4, and then also 5 pi over 4. So this is going to be, I'm going to write with some weird notation, like that. I know that makes maybe not a lot of math sense, but I think for what we're doing right now, it's okay. Now I'm going to take a look at each of these, and I want to see if either of them lie inside of the range for tangent inverse. This one does, that one doesn't. Why would I do what? You're talking to Michael? Is he drawing on your neck again or something? Oh, Mark was drawing on your neck. Did you like stab him in the hand afterwards? And that's what he's asking why you did that? It's because you're drawing on his neck. Okay. Are we good with how I've gotten to here? Okay. Last step. I'm going back to the unit circle. And I'm going to find pi over 4. Sine of pi over 4 is the y-coordinate. So I'd answer this as root 2 over 2. Feel okay there? Good. Amazing. You're so enthusiastic. I love it. What next? Lindsay? Sure. I realize now I probably should have just read the even ones to start with, since all of my questions have been from the even ones where you didn't have the answers to it, but that's fine. We'll do them all. It's cool. No big deal. This is my own fault. I did it for first hour. I started by reading the evens because I was smart then, and we got to the end of the day and I'm a lot dumber now. All right, so cotangent of cosine inverse of x. All right. So I'm going to start with the inside, and I want to start by thinking about x as a ratio. So I'm going to think about it as x over 1. So cosine inverse is going to give me an angle from the right triangle whose adjacent side is x and whose hypotenuse is 1. Are you okay with that idea? Okay. I can use the Pythagorean theorem to find that third side. That's just going to be the square root of 1 minus x squared. So this is going to simplify down to cotangent of theta. What theta are we talking about? That specific theta from that specific right triangle. So I remember that cotangent is adjacent over opposite. So in this case, I'm going to have x over square root 1 minus x squared. And that's it. Again, remember we talked about rationalizing denominators. I think really probably in the first semester you guys pestered me about this. We said we weren't going to worry about it unless everything was all numbers. So because this is an algebraic expression, we're not going to worry about rationalizing this denominator. You could if you wanted to. I would never mark it wrong. Well, we're just not going to worry about it right now because it's a lot of work. Or more work than I really think adds any extra understanding. Right? Doesn't help us understand anything more. Lindsay, does that feel okay there? Okay. So again, the idea on these ones is you use the inside piece to draw your right triangle, and then you evaluate the outside part using that right triangle that you've drawn. So the trickiest part is getting the right triangle drawn, and then from there it's usually pretty easy. else do you guys want to talk about here? $17 would be very similar. Should we do it? We can do it. It's okay. Why not? Why not, right? So sine of arctan of x. So remember, arctan and tan inverse are really the same thing. So just like before, I'm going to think about x as a ratio, specifically x over 1. So arctangent is the angle in a right triangle whose opposite side is x and his adjacent side is 1. Using the Pythagorean theorem, I can find the hypotenuse, which is just going to be the square root of 1 plus x squared. Okay. So I now have just sine of theta. What theta am I talking about? That specific theta from that specific right triangle. I know sine is opposite over hypotenuse. So that's going to be x over square root 1 plus x squared.
So do you always choose that corner for the theta?
You just need to pick wherever you're going to put your theta. Like I could have drawn my right triangle and put theta here, but then opposite would be here and adjacent would be there. And I still would end up with kind of doing the same thing. Opposite was x, and adjacent would be 1. But you'd end up with the same result. It doesn't matter which angle you pick to be theta, but you have to place your opposite and adjacent or whatever relative to wherever you picked your theta. So you pick your theta first, and then fill in the side lengths. But it doesn't matter where you put your theta, unless you put it in the right angle corner, which is wrong. But you wouldn't do that. No. That would be weird. Weird choice to make, right? I'm going to put it in the right triangle corner, or the right angle corner. It's like, no one's doing that. Do we feel a bit better about this topic? I know that some of you were grumbling about how confusing this section was. Does it feel less confusing? You suppose. If it still feels bad, look through some more of the homework. Like, look at it again. Come talk to me if you're still bothered by what's going on. Because this is an important idea. Like, when we get to solving, you're going to need to be able to find the right answer from tan, cosine inverse, sine inverse. You're going to need to be able to get the right answer out of that. And be able to find the answers that you're looking for on the interval that we're looking for. And find all of them on the interval that we're looking for. So it becomes very important that you're able to manipulate the answer you're getting from your calculator and find some other angles based on that answer. Yeah. Sure! The even answers. 2 is pi over 4. 4 is negative pi over 3. 6 is pi. 8 is negative 0.193 radian. 10 is 1.791 radian. 12 is square root 2 over 2. 14 is 1/2. 16 is 3.87. And 18 is x over square root 1 minus x squared. Michael? Of course. Does anybody have any additional questions now that you've heard the even answers? Does anybody have things that they're just generally confused on from this section that we just need to talk about that aren't necessarily linked to any specific problem? I know I asked you guys to read this and do these problems on your own, and I know that's maybe sometimes a big ask. That's why I wanted to take a day and do some unpacking. This probably would have been a 2-day lecture had we done it straight through all together, but we turned it into a 1-day lecture by doing it this way. What's the good news, though? No homework. What?